Welcome everybody to eClinching. eClinching is our Tox technology, our one-step joining technology for reliable electrical connections. Today we'll be going over as far as a range of competence for Tox, and then range of technologies and how that has translated down into eClinching connection mechanisms, some test results as far as quality, control, review, and insurance, review a few customer and applications, and then summary and some conclusion, and then we'll open up the floor for some questions. So Tox, we offer a wide range from component level, from our Tox power package, which is a pneumatic hydraulic cylinder, our electric servo drives, safety controls, process software monitoring, variety of clinching tools, machine controls, while offering a wide range of all the components. We have refined that into systems and offering a variety of different system level, from anywhere from our fine press, manual operations, all the way up into, fully automated, robot carried and fully automated systems. And then aside from that, we also offer, a custom, customer specific solution in order to ensure that, we meet your needs with a wide range of technologies. We do have a few key technologies: clinching, data clinching, e-clinching, riveting, inserting of functional elements or other fasteners. But it does branch out much further into, pressing in components, crimping, punching, net form and pierce, and then getting out even into checking, measuring, testing, wide range of different technologies that our components and our systems are capable of. We offer a wide range of technologies that revolve around e-mobility applications, from clinching, fastener insertion, and then riveting, whether it be from structural, the actual compression during assembly, electrical connections, and then actually testing of cells. So yes, a wide range all around, from battery to, throughout drivetrain. So like I said, we have a variety of different customers that utilize our different technologies for battery production. We have, whether it be from fasteners being inserted onto trays, clinching of actual closing, battery actually compression during manufacturing, and then also offer, riveting if you're looking for, at structural or specifically structural, and then down into inside where we start to begin to talk about e-clinching, or actual electrical connections. So e-clinching, as far as a process flow and how you obtain your electrical connection, it is a clinch process, but more revolving around the actual electrical connection, along with how robust that connection is, to ensure the longevity of your connection. So we do start by having the punch penetrating, compressing into filling out the die and forming your upper layer into your lower layer or layers, and ultimately finishing that joint out with a completed joint, completely formed into that bottom layer. Here, the punch and the die geometry are critical to forming that joint. We have a few different variations as far as what that die geometry looks like in order to, I guess, tackle a few different challenges that get posed throughout different applications. We offer our round point, our micro point, which is a much smaller die and much smaller punch. And then we have our E-twin point that helps to withstand different torque challenges that may be present in an application. You can see here, as far as a bottom thickness, our X dimension is our critical measurement that we are looking for to ensure that we have displaced enough material and have properly formed our joint. So very frequently we get asked questions on longevity and how do we combat the relaxation of materials where we actually lose that electrical conductivity. And here it goes through our development of that punch and die combination in order to prove out that we have a reliable connection that over time does not relax. We do not have any material material properties that change that allow for a higher resistance or a loss of conductivity throughout your electrical circuit. So with that, we are able to, you can see a chart on your left-hand side that becomes much more unstable. And then as we form our joint and we can really start to lower that electrical contact resistance, that as you have the elastic portion of your material relaxes back, or over time you do not have any loss. And so we target to have a consistent, reliable electrical connection throughout the life of the joint. So what you're seeing as far as a fundamental of that electrical conductivity, between two faying surfaces, you have your actual contact surfaces, and then you'll have your quasi-metallic surfaces and then surrounded by fully insulating contact surfaces, whether that be through oxide layers, contaminants, debris, whatever that might be. And so the real target is how do you lower that resistance by increasing the amount of that micro contact? And so how we get that is through surface enlargement. And so as we deform the material, that enlargement of that actual contact surface increases, and therefore you have a reduction in your joint resistance. So here's an FEM analysis of what's actually happening inside of a Tox eClinch joint. So you see on the left here, as the punch completely meets its lowest position, its highest force for what is prescribed for that joint, you have the highest level of stress around the bottom part of your joint and then into the neck portion of your joint. And as you begin to return your stroke, you have a lowering in stress throughout the entire joint. So that therefore that's not ensuring that electrical contact, the surface area, the true surface contact. And so the real target here is how do we leave the highest level of remaining mechanical stress within the neck in order to ensure that true electrical contact. And so that deformation, that amount of surface contact enlargement is key here. So to further explain a little bit more where you So you can see on an FEM analysis of the surface, I'll say the surface distance of the two faying pieces of material, as you deform and you elongate that surface, that breaks up the oxide layers and it smooths out the roughness, and it'll increase the actual contact area. And in the neck area, we're seeing anywhere from 250 to 300% increase in that surface enlargement, along with that bottom area. But it's really key that it's within that neck area because you're able to withstand that residual mechanical stress, and to ensure contact between your two layers of material or between your layers of material. So what you see here is a true example. And so you have, again, that high level of mechanical stress and that surface enlargement that is breaking up. You can see on the bottom right-hand side, you can see the breaking up of those oxides, and the stretching of that material, exposing, raw parent material, where it's actually making, excellent contact between raw parent, the lower material. In this case, it's aluminum and copper. And so what you see here is where we have made that joint and have done a cross section in order to evaluate that it is, a very good contact, and then actually separated the two pieces of material so that way we can see. Here you have the actual aluminum, the bottom layer. And then what we're seeing is that contact point, those high contact points, we're actually getting an excellent bond between the two, that when trying to mechanically separate the 2 points, you can see that you're getting a mechanical joining of 2 surface layers of material, where you can actually see some deformation of the 2 materials trying to pull them apart. And here you can see, the 2 layers of material in the beginning not having excellent surface to surface parent material contact, and after that deformation and all of that strain that has gone into the material, that we have significantly increased that surface to surface contact. So measuring electrical conductivity, measuring the resistance within the material. So one of the first things that we evaluate from a material standpoint as we go through the actual development of the joint, we start with a baseline of what the actual parent material resistance is, whether it be in the as received condition or what the final production intent condition will be. And we get a baseline of what that just raw material resistance will be. And then just to kind of explain really how easily an electrical joint can be as far as the level of resistance. Here you have, I'll say, a 0 contact force, so it's just lightly joining. So you're getting a very low surface to surface contact, and you have high insulating factors in between, into a little bit higher of a force connecting the 2 materials. And then you can see how that really starts to drop as you start getting, you start putting in that mechanical stress and getting that surface enlargement. The contact between the materials is increasing, and you're getting a very, very good electrical joint just by that surface enlargement. And so then how do you retain that? How do you keep that joint within? And it's through that final forming of that top layer into that bottom layer, in order to retain that mechanical stress. and hold those two materials tightly together. So you can see here from a mechanical, or I'm sorry, from a base material resistance down into an optimized eClinch joint, you're looking at almost a one-to-one comparison between what your natural resistance is in your material to what your joint is. So you have no loss. So over time, you end up having, you can have aging of material or a relaxation of material. And what you really need to do is you need to set up and find a joint that can combat the effects, naturally within the material, especially at elevated temperatures, to ensure that your connection is still good. So here you can see over time, and so there's a few different joints on this chart. By the way, you'll see on the left, it's a quality factor. It has to do with what the joint resistance is in comparison to the parent resistance. So generally, we look for a quality factor of between 1 and 1.5. It all depends on what your application requirements are, and then also what the condition of the materials are. But it's not uncommon for that joint to be as close, and in some cases it can be better just because of that surface enlargement. But you can have an excellent quality factor where the resistance in the joint is actually lower than the material, and that has to do with that surface enlargement. But yes, you can see here, you can end up getting long-term stable. So over time, any aging mechanisms, stress relaxation, electromigration, interdiffusion, grid deformation, whatever is happening over time, it can be combated by holding on to that, having that residual stress within the joint, and also not forming an intermetallic bond. So here you can see, as far as corrosion, there's also excellent performance here. We have closed geometry, preventing moisture from entering the joint, keeping that out for a number of cycles, and then over, a long corrosion, study or a test, in order to show that actually corrosion is not able to penetrate and severely degrade the electrical, conductivity of the eClinch. So for a temperature analysis, you can see under thermal, thermal scope, we're able to see, or not able to see, the actual location of that joint while under load, in order to ensure that that's not a weakening or a location where you're going to end up having an increase in temperature. So for process monitoring and ensuring that while actively forming your joint and in production, we have a variety of different options that we can monitor, but primarily our target is that X dimension, and so it's proportional to the resistance and inversely proportional to those holding forces. And so as you, I'll say, decrease your X dimension, you're having a significant increase in your holding force within that necking area, where you're able to ensure that you have that residual mechanical stress. So we can also offer a process monitoring with windows, or envelopes, in order to ensure that key points along that curve that they're being met appropriately, so that way if there is any issues or anything that's popping up while actually forming the joint, we can flag appropriately in order to ensure, and also be able to detect, changes over time, anything new, imposing itself on the process. So we also offer, a tool check. So after each joint, we can come down and we'll actually check the integrity of the die. Well, we do offer some options as far as for monitoring the punch, but this is primarily, if there's any breakages or any intrusions, any debris, anything in the die that can adversely affect the actual setting of the joint, or what the quality of that joint may be. We can check in real time. Several customers use this after every job change to ensure that the prior job is acceptable, and then be able to ensure that the tooling is ready for that next job. Before we get into customer applications, I just wanted to just remind, if anybody has any questions, anything, to please go ahead and put it in, and Ashley will be able to bring them up at the end, and we'll be able to answer all your questions. So, as far as customer applications, so we have obviously from anywhere from OEM to tier 1, wide range for electrical connections, whether it be pre-fuse box in passenger cars. We have high voltage applications within the battery, heating elements, actual battery cell connections, terminals. We'll go over a little bit of some size and what limitations may be, or I should say, wide range of materials and applications or thicknesses. Right. Oops. So here you can see, as far as a couple of different joints here, we have an aluminum to aluminum, copper to copper, and then a mixed material. We're having a joint between the dissimilar materials. See directly on the bottom where you're having solid bus bars. So from thin materials to thick materials. On the right, you can see there is a little bit of preparation for the wiring harness, but stranded materials or layered materials, they can be prepared well enough that they also can be joined in order to connect that battery wiring harness into the circuit, or I should say connecting the battery into the rest of the circuit. So as far as range of sheet metals, so if you are looking at a thick to thin, which is the preferred for clinching and e-clinching, you can have a very large difference, a ratio of 4 to 1. That allows for us to actually form the material, and that thin bottom layer is actually able to be formed up around that thick layer. That helps with forming in the die in order to ensure that there's enough elongation and surface enlargement for that bottom layer to make contact. And then as you get into transition from thick to thin into same materials, obviously same materials are certainly acceptable for a 1-to-1, but then you start running into a thin to thick. The applications do arise, so they are certainly possible, though it gets a little bit more limited, but it's certainly capable. We can stretch the boundaries slightly in some areas, and that's where you can see those two gray, the lighter gray areas, in order to meet that. Now, if there are instances, which every day we challenge the the guidelines, but if there are, then further material thickness accommodations can be investigated. That's no problem. We are certainly looking at thinner and thinner, especially for our micro point, in order to ensure that we can meet that application. So for material thickness, you can get a range of different Tox points. So on the left, you can see round points, what flange width needs to be, or from a total sheet thickness, kind of specifies really what the limitation. Obviously, the smaller is the better, as long as the electrical connection is maintained. But as you increase that material, you can get larger and larger points that ensure that you can have a sound and robust electrical connection. So for a range of service, from consulting to introduction into e-clinching and making mechanical electrical connections, as you go through application development or material development, whatever you're looking for, we can certainly look at development in order to suit your needs of what you're really looking for. Into production, obviously support in production, failure analysis if there's issues with your eClinch, or what mode of failure may have arisen, into installation, and obviously after sales support. So yeah, certainly able to review and analyze any of your e-clinching needs. To summarize, what means Tox e-clinching for your application? So e-clinching is a gas and liquid tight joining technology that leads to high corrosion resistance. You can have the same or mixed dissimilar material layer combinations. You can have connections that are of plated materials. This often leads to applications that do not require surface treatment. So e-clinching is a low resistance and the high conductivity over the lifetime is ensured. E-clinching is applicable to connect heat sensitive battery elements, has no heat, no vibration. So there's a wide range that e-clinching can be applied to. And then finally, there's no intermetallic phases that you're joining for dissimilar materials, which obviously aids with the low resistance and the high conductivity. So again, gas and liquid tight joining leads to high corrosion resistance. The same or mixed material layer combinations are possible. Connection of plated materials without surface treatment. A low resistance and high conductivity over the lifetimes ensured. Applicable to connect sensitive battery cell elements, as there's no heat or vibration applied. And then no intermetallic phases by joining dissimilar materials. I'd like to thank you that we have been doing e-clinching for more than 10 years. Therefore, we are very excited in order to investigate and explore whatever applications that you are interested in. I do invite you, if you were to look at our white paper that we have on e-clinching, learn a little bit more. There's quite a bit more details into the process and into the development of e-clinching. So, and then here I do have our business development manager, Frank Ortman, based out of our Weingart, Germany headquarters, handling all the business development for our e-clinching technology. So